We present a novel approach for axis and scene-level reflection and rotation symmetry detection using a group-equivariant representation. Existing methods are limited to object-level symmetry detection or generate heat maps showing likely symmetric regions without explicitly predicting the symmetry axis. We present a unified framework that detects symmetry at both the axis and scene levels. It robustly handles both reflection and rotation symmetries through group-equivariant representations, and it leverages explicit feature matching to achieve precise symmetry correspondence within the equivariant feature space. At the core of our approach are two key principles: matching and equivariance. So first, why do we need matching for symmetry? Take the example of reflection symmetry. We can test it by cropping a region in the image, drawing an arbitrary axis, flipping the image across that axis, and checking whether the two sides match. If they do, we can regard that axis as a reflection symmetry axis. In other words, reflection symmetry is fundamentally defined by matching, and this concept naturally extends to rotation symmetry, where the matching occurs around a rotational axis. This matching strategy can also be applied at the feature level. However, common neural networks are not robust to rotation or reflection. To address this, we use a group-equivariant network, which produces features that transform consistently with the input transformations. Formally, for a group G-equivariant network F and a transformation G in G, we can define equivariance as F of sigma 1 of G applied to X equals sigma 2 of G applied to F of X. Also, the group-equivariant network generates group-specific features that vary with orientation, allowing us to detect symmetry axes corresponding to specific directions. With this motivation, our method is built around two main components: a matching module, shown in yellow, and orientational anchors, shown in pink. First, the images pass through a D8 group-equivariant network to generate D8 equivariant features. Next, these features go through each matching module to produce matching features. Matching is done with multiple receptive fields for scale robustness. Finally, for reflection symmetry, the network predicts the axis center probability, the axis orientation, and the axis length after the orientational anchor expansion. For rotation symmetry, the network directly outputs the rotation axis after the matching stage. In reflectional matching, we flip the feature both in the spatial dimension and in the group dimension along the axis corresponding to the C8 group. We apply this process to the entire feature space in a sliding window manner, and it produces a dihedral group equivariant but reflection invariant feature. A similar strategy can also be applied to rotational symmetry. The dihedral group contains group-specific features representing 8 orientations spaced by 45 degrees, along with their reflected counterparts. We first merge the reflection components using a simple MLP-N. Then we merge the orientational features that point in opposite directions, since from a line perspective, they can be considered the same. Finally, each orientational feature is used to detect reflection symmetries within its corresponding orientation interval. This table highlights the effectiveness of our method, as applying the orientational anchor expansion and matching strategies significantly improves performance, showing a large performance gap. Our method also outperforms state-of-the-art approaches in terms of F1 score, and this improvement can be clearly seen in the precision recall curves. Thank you.